My name is Jangho Park, and I'm a postdoc researcher in CCSE. Today, I'm going to talk about how we predict time series future groundwater level with machine learning. So why do we focus on water research? As you know, water is a scarce resource, and recently, extreme water shortages observed in recent years. It means that we need sustainable water management. So as a first step, we are going to try to predict future groundwater level with machine learning. To do that, in this research, we try to replace high fidelity mechanical simulation to neural network because simulation typically takes a long time to get result and we need high performance computing. And also we try to replace traditional time series methods such as ARIMA model to neural network because this kind of parametric time series model cannot capture highly complex nonlinearity. And we are going to use hyperparameter optimization technique to improve quality of predictions. Here, hyperparameter means parameter whose value is set before the learning process begins. And it's widely known that the performance of neural network is highly depends on hyperparameter. So we are going to try to find best hyperparameter for time series prediction. Okay, here, because we are working with time series data, we have several challenges. I'm going to show two challenges here. First one is then how to set input to have historical information with time series data. And also next challenge is then with time series data, how to find the best hyperparameters. To do that, we first augment temporal information into hyperparameter set, and then we find the best hyperparameter with a derivative-free global optimization approach. We have two contributions here. Our proposed method can provide fast and accurate groundwater level predictions, and also our proposed method can be used not only for groundwater level prediction, but also for any time series prediction problems. Okay, as you guys already know, there are a lot of neural network. For example, multi-layer perceptron, or convolutional neural network, or recurrent neural network, and long short-term memory recurrent neural network. But in this research, our focus is not only one neural network. We are going to tune any kind of neural network. So it can be called model-free hyperparameter optimization approach. Let me briefly explain what is hyperparameters for neural network. Okay, this is some hyperparameters for multi-layer perceptron. So for example, we should decide how deep our neural network is. And also if we decide number of the deeps, then we need to decide how many nodes in each layer. And now let's look at how we use time series data set. Because we use time series data, we should make an input to have historical information. We use lag table to an input to have information. So for example, we have 5 daily observations for temperature, precipitation, and groundwater level. And if we set lag as 1, we are going to use this lagged input to predict this next day. It means that on the current day, we use 1 day ago historical information to predict the next day. It means that we are going to have a total 3 input size for neural network. If we change the lag as 2, on the current day, we are going to use 2 days ago historical information to predict the next day. It means that we are going to have 2 total input size to our neural network. But here, as you can see here, there is trade-off between historical information and number of input samples. For example, if we have larger lag, our one input has more historical information, but we are going to have only 2 samples. If we reduce the lag, we can have some less historical information in one input, but we can have larger input samples, 3. So here, we should find the best lag to make to handle this trade-off between historical information and total input size. Yeah, this is example of lag and multi-layer perceptron. As you can see, if our lag is 1, we are going to have 6 input nodes, and the first prediction starts from day 3. If we change lag as 2, we are going to have 9 input nodes, but our first prediction starts from day 4. Yeah, so actually lag determines the input structure of a neural network, and also lag determines the amount of historical data in an input. So lag is perhaps one of the most hyperparameter in neural networks for time series prediction. Oh, yeah. So traditionally, this decision for lag was performed with pre-processing. For example, you can set any lag and then increase 1 by 1 until you get the best result. But even we don't know when we start and when we stop, so we think that's not a good idea. The second approach is we can use traditional time series analysis. First, we can look at the autocorrelation function and partial autocorrelation function plot. And then we can decide order for autoregressive function. And then we can use that order for our lag. But we cannot guarantee this lag is best for neural network. So we are going to consider lag as one hyperparameter. Yeah, typically the state-of-art software for machine learning, TensorFlow, which is developed by Google, and PyTorch, which is developed by Facebook, do not support this auto-selection of the lag. So we are going to put lag into the hyperparameter. Now we define our hyperparameter optimization problem into bi-level optimization. It means we are going to solve 2 optimization problems. Yeah, the upper level optimization problem, we minimize loss function L over the hyperparameter theta with optimized neural network weights W star with dataset D test. An example of loss function is mean squared error, which is average of square of difference between predicted test value and true test value. And this predicted test value can be easily calculated with this optimized neural network weight. Then how to get this optimized neural network weight? Here, on the lower level optimization, we solve this minimization problem. And here L is loss function for training of a neural network. To get the optimal weights, we can use TensorFlow or Google the PyTorch. Okay, to solve that the bi-level optimization, we use algorithm for computationally expensive this algorithm. So we first map the finite set of possible values to a sequence, and then we select N0 hyperparameter set. For each hyperparameter set, we get the optimal weights, and then based on this optimal weights, we get the loss for each hyperparameter set. It means we have N0 hyperparameter loss pairs. At the step 3, now we find a next good hyperparameter set and get a new hyperparameter loss pair. To do that, we first approximate the lower level, upper level loss function L with currently available hyperparameter loss pairs. And then to select the next point, let's look at this one. To approximate function, we can use radial basis function or Gaussian process models. And then to choose the next point, we can use stochastic sampling for radial basis function, or we can use expected improvement for Gaussian models. And we repeat step 3 until the termination condition is satisfied. In our experiment, we simply set termination condition as the maximum iteration, for example, 50. Okay, yeah, we test our proposed procedure with groundwater prediction in a well in Butte County, California. Yeah, here we assume that we have training and test data from 2010, March 24th to 2016, February 18th. And then we assume that we are going to predict the groundwater level from 2016, February 19th to 2008, February 28th. And here, for the experimental purpose, we assume that we don't know the value for this one. And now we assume that we have daily prediction for groundwater level and precipitation, temperature, and river flow. So here, in terms of our bi-level optimization, as you can see, we are going to use historical data to get optimal hyperparameter. And then based on optimal hyperparameter, we retrain neural network with all the data. And then we predict the future, which we assume that we don't know future. This blue line. Yeah, let me first discuss result without hyperparameter optimization. Here we use multi-layer perceptron, which I assume that lag is 7, and the hyperparameter like this. As you can see here, the results are very bad. So if we, this one is the number of layer. So we can use deeper layer. Yeah, I tried with deeper layer. And then, we can get better result. Now, how about increase the lag? Yeah, I can increase the lag to 108. As you can see, the result looks very good. Not very good, but relatively good. Then, how many tests you have to get the best result? Yeah, let me show this table. Yeah, for I'm not going to through details, but I'm going to show why we need hyperparameter optimization. Let me first explain what is epochs. Epochs means the iteration to get optimal weights for neural network. So it is known that if we have 2 less iteration, you can get the poorly fitted values. But if you have 2 large iterations, you are going to get over-fitted values. So we have to choose reasonable epochs, then how to choose it. And for example, the layer. As I showed that if we increase lag, the layers, I was able to get better result. Then, how many layers do we need? So deeper layer is better. Yeah, we cannot say like that. And also, now I explained each hyperparameters, but we should consider the combination of each hyperparameters because we don't know the interaction between each hyperparameters. Now, if we think about all possible combinations, for LSTM, we have, this is not all hyperparameters, just we considered in this research. Even this restricted number of hyperparameters for LSTM, we are going to have 480,000 cases. For multi-layer perceptron, we are going to have more than 7 million test cases. And for RNN, we are going to have more than 2 million, and for convolutional neural network, we are going to have more than 30 million cases. So can you test all those cases? Definitely no. So that's why we need hyperparameter optimization here. So now I'm going to show result with hyperparameter optimization. So as I said, we put lag as the one of the hyperparameter, and then this is the final hyperparameters with our hyperparameter optimization problem. As you can see here, compared to our manually setting the hyperparameters, we are going to get pretty good result. Actually, the error of this prediction is less than 3.28 feet. And as you remember, I used 6 layers to have better result. But here you can see, our hyperparameter optimization doesn't choose always the deeper lag. So we can say, we cannot say deeper network is always better. Okay, this is my conclusion and future research. Here we automate the lag and neural network structure selection simultaneously with the derivative-free global optimization approach. To do that, we first put lag as a hyperparameter, and then we use derivative-free global optimization. For example, radial-based function with stochastic sampling, or Gaussian process model with expected improvement. As I said, yeah, we can predict future groundwater with the average loss is less than 3.28 feet. Actually, this is just 10.68% of the observed groundwater range. So we can say our prediction is pretty good here. Yeah, we have many other future research directions, but here I'm going to show just one possible future research. So as you know, if we collect data, typically there are a lot of missing data. For example, if we can have 1 year missing, or we can have 2 year missing, or we can have 1 week of missing data. And typically, the traditional approach should fill that gap. And then based on that predicted value, and then we predict the future value. But we think estimate with predicted value might distort the reality. So we are going to try to predict future without that gap filling. Does it make sense? Yeah. So our preliminary research showed that, yeah, we can predict pretty well with missing data. Here, this red line indicates future prediction with full data set. And here, the black line indicates we train model after remove this 1 year of data. And then we can predict, we can capture the trend pretty well. Okay, this is my last slide. And those are key references. And thanks to Julie, Litik, Deb in CLD, and Charu, Bhavna, Boris in ISA. Thank you.
Questions? I have a question for the same 15. Yeah, each of the samples, are they done one every day? Is there one sample per day?
Yeah, we have daily. Yeah,
so
daily.
Do you think it's a coincidence that the number of lag optimal is a year, like 360?
Yeah, maybe that. Yeah, but yeah. So we try to not put our idea into choosing. Yeah. We just want to choose lag without any knowledge.
Yeah. I just find it funny.
Yeah.
So have you tried your trainer model to test the 2019 data, so where the RMS may be larger than the 2018 data?
Can you repeat?
I mean, like, so your validation data is 2018. So have you tried your trainer model on 2019 data?
Oh, yeah, not yet.
So where the RMS be larger than the current one you got?
I'll talk about it.
Yeah. Yeah, next presentation. Thank you. Yeah, sorry.
Just on your last future research, you mentioned that when you remove some of the data, you're still able to predict quite well what's happening. But do you know how much you can remove of it until you kind of failed to predict that?
Yeah. Currently, I just moved 1 year. Yeah, but I didn't check how many days I can remove it. So maybe I can check the minimum possible data set or maximum missing value to predict future for later. Yeah, currently, I just remove 1 year.
Yeah, it's already a lot of data.
Seems like. And do you know if it's influenced by when you remove data? Like if you
sure.
remove closer to today, if the prediction changes?
Yes. In my first couple of slides, I explained lag, and we change each input to the lag at the table. Yeah. For example, if we assume that we don't have these values, it means that we cannot predict from this one. Yeah, we can predict if the lag is 10, we can predict after 10 days because we need input data. But here, it doesn't affect to here.
Now you.
Yeah.
Will you please go back to slide 5?
5.
1, 2. Yeah, so I guess I got a little bit confused about how you divide the data into training and test here, assuming, because I think my knowledge of validation is usually the part of the training that I use to find your hyperparameter,
Yeah.
right? Like, yeah, just maybe you just elaborate a little bit.
Yeah, here, we first assume that we don't have this data for groundwater level. We assume that we know precipitation, temperature, and river flow. We can get from any kind of simulation data for this one. So to run the hyperparameter optimization stuff, we remove this one. So here we just divide 4 years of training for typically neural network stuff, and then to approximate loss function for our upper level. For that purpose, we use these 2 years of test data.
So you use the test data to
Yeah, we don't use test data for we don't use test data during the training. We just use train data for training.
Okay. So my question is, which part of data do you use for looking for the hyperparameter?
Yeah, let me explain. This part are going to be used for choosing best hyperparameter, and this one is going to be used to find best weight. Yeah, this training data is going to be used to find the best weights, and then this weights is going to be this another loss function upper level, and then we approximate this function with this test data. Does it make sense?
Yeah. So.
Yeah.
Okay, we can talk about that, but I think usually once people say validation, they mean like part of the data they separate from, which meaning that you just look for cross validation to find the best parameter you want to use. Right? So when you say like the validation is the future data, you assume unknown, and it's sort of confusing for me.
I see. Yeah, maybe this part is, in your sense, this is part of validation. Yeah.
And another question is about, so it looks like the data performs a little bit noisy. Do you assume, personally, like there will be noise in this real data, right? Then any process you have done to filter noise or?
Noise. Actually, the data set maybe, a good question. I got the data from the other department here.
I think the collaborators in EDSA, Boris Jangho, he has a huge background of data and stochastic and whatnot, and he cleaned the data. So he did a QA/QC of the data to remove outliers. Now the question you may have is like you only have a point per day, and there should be some uncertainty on the point, right? That's not. We really have just this one point to work on. And the data is really out of control. The outlier was filtered out. Okay. Data that was missing got filled in with a gap filling algorithm. Okay, that's good. Thanks.
Can you say, so the groundwater managers who are interested in these kind of predictions, what actually would they consider to be good results? What are the questions they ask?
Yeah.
I can answer.
I think his question is why this is good. This number.
Well, no, my question is what's the actual question that the groundwater managers want to answer?
From the groundwater managers' perspective, they are worried about where the future groundwater level is going to be. And with the lack of data and everything, it's difficult to even figure out from their point of view, even the groundwater level, is it just going up or down? So now given just meteorological variables and temperature and precipitation data, we are now bringing down that error of going up or down the next year to 3.2 feet. So that's like a huge benefit for them to now run different what if scenarios, what if climate scenarios in the future of, given everyone else is, the humans are doing the business as usual approach, what would the groundwater turn out to be in the next 2 or 3 years or 4 years in the future? So for them, that knowing that is very important, because then they can come up with, okay, we then need to cut down some of the things or improve groundwater levels.
Okay, thank you. Any other questions?
One last question. You have 3 parameters, input parameters in X, and like if the ground level guys come to you and say, okay, we want to like change one of our sensor, like to be twice the resolution maybe, and they ask you which one of these should be twice better in terms of resolution, can you help them say, okay, you should like change precipitation because that's the one that controls the most my prediction, and so maybe yours. And can you like have a feedback like that saying, okay, you should improve your temperature sensor?
So you think your question is which variable is significant for prediction?
And if you have twice much data for this particular input, that improved a lot.
But the number of data set, we should have the same. For each sample should have the, because when you feed data to the neural network, we assume that the input nodes are same for every iteration. So each iteration should have the same number of nodes. It means that each data should have the same length of the data set.
Even if you do some kind of filtering.
Maybe that's might be good next research. If we have more data for temperature, then we might do something better. Thank you.
Okay, thanks very much.